In this section, we're going to look at the reactions of dienes. But first, let's just review a couple of reactions from Organic 1. If you take an alkene and react that with an acid like HCl, HBr, or HI, you're going to add the hydrogen and the halogen across this double bond in a Markovnikov fashion, meaning the hydrogen goes onto the carbon where you have more hydrogen, the halogen goes onto the more substituted carbon. If we take a double bond and add a halogen like Cl2, Br2, or I2, then both halogens add across that double bond. So we end up adding an X to this carbon and an X to this carbon. So what we want to think about now is what happens if we do these similar types of reactions to dienes instead of simple alkenes. So as a general preview, what if we take an isolated diene and add HX to that? What products can we expect to get? Likewise, what if we take a conjugated diene and add HX to that? What products can we expect to get? So that's what we're going to be taking a look at in this section. If we're dealing with an isolated diene, what our focus wants to be to predict the product is going to be getting the most stable carbocation intermediate possible. One thing to keep in mind is that this can get messy if you don't have good selectivity, and I'll show you what I mean by that in a second example. So let's start with this first example where we have an isolated diene reacting with HBr. What you want to do is look at all of the carbons that are part of the double bond. So we have here, 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 and here. And think about reacting each double bond with a proton, H+, and the resulting carbocation that you would get. So if we were to draw this out for each of these, we could get a tertiary carbocation here, secondary here, secondary here, and secondary here. So in this case, we're going to have good selectivity. And that's because getting this tertiary carbocation is going to make it selective to brominate at that position. So what we'll do is use this double bond on the left, and we'll do the reaction. So these pi electrons will come over and take this proton, and you'll lose Br from the proton as a leaving group. Now let's draw the intermediate. We end up putting the proton on this carbon, because what that gives us is in our intermediate the tertiary carbocation, which is the best we're going to be able to get in this example. We also end up with the Br minus. So now what happens from here? You have the carbocation and Br minus. Br minus acts as a nucleophile and adds to that carbon. So I'm not going to draw the hydrogen in, we'll leave it implied, but we've added the new Br, and this is your final product. In this example, we used one equivalent of starting material, one equivalent of HBr. If you had used two equivalents of HBr or an excess, then you would also get a reaction at the other double bond. This one would be a little bit slower because you don't get the tertiary carbocation, you would get a secondary carbocation. Now let's look at this example where we're using an excess of HBr. Like before, the first thing you want to do is analyze all of the carbons that are part of the alkenes and figure out what carbocation you could form. We could form a primary carbocation here, a tertiary here, secondary, and secondary. So our preferential reaction is going to take place at this carbon where we'll get the tertiary carbocation. But keep in mind we're using an excess of HBr. So we're going to use the first equivalent with this double bond, and since there's an excess, we'll have a second equivalent to react with this double bond. So the first equivalent, we add HBr across the double bond. Let's draw the product. I'm not going to draw out the mechanism for this example. So we add the hydrogen right here. I'm not going to draw it in. You would get the carbocation here, and that's where the Br will end up. Okay, but now we still have HBr floating around that can react with the second double bond. And it will. But in this case, you're not going to get any selectivity at one side of the double bond over the other, because both have the same substitution. Both would give you a secondary carbocation. So that means we're going to have equal likelihood of reacting at either site. And that means this is going to lead to two different products. So in one product, we'll get the Br here. In the other product, we'll get the Br here. So when I said this could start to become a mess when you don't have selectivity, this is what I'm talking about, where you can get multiple products.